The Prime R4 router is a hardware-integrated optimization framework designed to push extreme data loads through consumer processors. Instead of relying on a massive server farm, it facilitates up to 1 terabit per second of localized data flow directly on a standard Apple M1 chip. This chart outlines the hardware performance benchmarks from the Prime R4 research report. Looking at the M1 proxy row, the router achieves 1280 gigabits per second of peak throughput. It maintains a synchronization latency of 0.15 milliseconds, with a buffer overflow rate of just 0.0002%. To sustain that throughput on local silicon, the system maintains a 97.4% CPU cache hit ratio. That specific metric exceeds the established computational limits for local large language models, which typically encounter a severe memory bottleneck long before reaching these speeds. These benchmarks suggest that the standard throughput bottleneck is not an inherent hardware limitation, but a result of how data is coordinated. By shifting the routing logic directly into the processor's cache architecture, the system sustains the density of information required for high-dimensional models on local hardware. Standard deep learning currently relies on mixture of experts, or MOE, architectures. These systems direct data using learned gating matrices, parameters that must be trained to decide which specific parts of the neural network activate for any given prompt. Learned gating scales quadratically. As models grow, they suffer routing collapse, overloading specific nodes while alternative pathways sit idle. Because idle parameters occupy space, this consumes finite RAM. On local hardware, the model hits a memory cliff, triggering system failure. The Prime R4 router avoids this cliff by eliminating learned parameters. Instead of using Euclidean logic or traditional lookup tables, it routes data using a fixed, non-Euclidean geometric partition. To shatter the memory wall, the architecture abandons standard TCP/IP routing tables. The data flow transitions into a continuous geometric manifold, utilizing spatial geometry as a native routing engine. Before the R4 can calculate high-dimensional geometry, it must establish a physical hardware layer designed to prevent standard data packet collisions. It achieves this through the hex-hive modulo 6 topology, mapping hardware MAC interfaces exclusively onto prime number coordinates. Parallel phase transport channels lock to these distinct primes, defined by 6K plus or minus 1. Due to prime distribution in this class, these channels never intersect. This prime-aligned addressing creates a deterministic, collision-free physical substrate. This discrete base is mandatory to support the continuous, non-Euclidean mathematics running on the software layer. While the physical hex-hive grid is laid out in 2 dimensions, standard flat space logic creates geometric bottlenecks as the network grows. To maintain sublinear scaling, the routing must move beyond the congestion points of a traditional 2D mesh. The foundation for this non-Euclidean routing is the 1982 discovery of exotic smooth structures in 4-dimensional space. These structures reveal that multiple, non-smooth differentiable manifolds can coexist within the same topological space. The router applies this through the hop angular routing protocol. It discards flat space addressing tables and embeds network nodes onto the surfaces of high-dimensional hyperspheres. To guide data across this curved space, a coupled field approach driven by the Laplacian signal flow equation balances graph adjacency with continuous hyperbolic distance. It calculates routing via zero-weight geodesic evolution, letting data naturally follow the space's mathematical curvature. By letting pure geometry dictate the path, the system achieves a sublinear scaling footprint. Specifically, compute requirements scale at k to the power of 0.572, drastically reducing the overhead plaguing traditional large language models. The remaining challenge is how a local Apple M1 processor can physically execute these hyperbolic functions without hitting a memory bottleneck. Standard hardware relies on static memory allocation, writing data to fixed RAM addresses. When forced to process dynamic, non-Euclidean data loops, static allocation creates severe latency regressions and memory cliffs. To eliminate these barriers, the R4 router replaces static allocation with phase-based continuous buffering. The system reads the localized curvature of the mathematical manifold, using that information to preemptively cache only the specific local vectors required for the upcoming cycle. This geometric predictability allows the system to dynamically prune up to 30% of standard memory requirements. This is the exact mechanism that makes the 0.15 millisecond M1 benchmark physically achievable. The primary architectural manifestation of these mathematical principles is the geotransformer V4.2. The model utilizes a 48-layer hybrid stack, splitting operations into two parallel streams, syntactic flow and semantic geometry. These pathways cross-attend at exactly every fourth layer. This geometric cross-stitch preserves grammar, while the semantic stream conducts complex non-Euclidean reasoning. By applying these strict geometric constraints, the geotransformer can operate with a compressed 70 billion parameter footprint, while matching the empirical processing performance of a 140 billion parameter brute force model. While the physical data is compelling, the R4 framework faces academic scrutiny regarding the integrity of its mathematical logic. One major critique is the logical conflation vulnerability. Critics argue that physical Lorentzian manifolds, which describe continuous spacetime, cannot simply be equated to the logical network loops found in a digital system. There is also the circularity critique, noting the paradox of requiring pre-calculated prime displacement maps to navigate the router in the first place. Despite these theoretical gaps, the physical benchmarks demonstrate that capabilities like semantic compression and logic routing are not external software add-ons. They appear as emergent properties arising directly from the underlying geometry of information.